So it's a pleasure to be the first chairman of this session of the third week of MLQC4Dyn. The first speaker of the session is Michael or Michael?
Michael.
Mike Martaler, who will talk about simulating open quantum system with quantum computers. Thank you very much. Thanks. The stage is yours.
Yeah, thank you. Exactly. So the title was already read. Yeah, it's about open quantum systems. So in general, as Dario already pointed out, when we talk about quantum computing, a good thing to think about is how we use the quantum computer to solve the Schrödinger equation, and that's going to be it. And then the question is Schrödinger equation for what? So what is the system we want to consider in our Schrödinger equation? And let me now start a little bit to motivate why we consider open quantum systems. And let's start this by comparing to, let's say, the workhorse algorithm that currently everybody, or let's say approach that is everybody is using, namely variational algorithms or variational approaches. And while they are really convenient, for small scale examples, HQS also uses them all the time to make small examples. To make something that is in the quantum advantage regime, meaning beyond what classical computers can do, they will not work. Let's review this a little bit. What is a variational approach? So what we do is, in a variational approach, we initialize all the qubits of a quantum computer in a kind of trivial way, which is indicated here by this state size 0. And then we act with certain gates that form a unitary operation onto this initial state, and the gates are parameterized with the parameters theta. And now it comes to final state, and then we measure some type of operator average at the end and try to minimize it. And kind of the minimized operator average is the solution. And if we do this kind of for a molecule, one thing to note is that we have to make first an initial calculation, get some a good starting point for an initial set of orbitals, and then choose a set of orbitals that we map to the quantum computer. And this can be a rather small quantum computer, a rather small set, 50, 60 orbitals maybe, that we map to the quantum computer. And the rest, well, we have to also think about how to handle the rest or what to do with it. And so let's keep in mind, normally the mapping is that one spin orbital goes to 1 qubit. So if you have 60 or 80 qubits, this would mean 40 spin orbitals, 80 spin orbitals or 60 spin orbitals. And now let's consider this in the context of the challenges with variational approaches. And let's start with one. This is the most fundamental, and it's called the barren plateau, kind of barren plateau problem, that if you try to minimize such an operator average, often kind of the time you need scales exponential in the number of qubits. Of course, this cannot be shown that this is so in all generality for every possible operator you could choose, but it still seems pretty fundamental. And given how many practical challenges we have when we want to run anything on a noisy intermediate scale quantum computer, the fact that we also have to deal with something which is probably fundamental as a challenge is pretty annoying. Then come more the practical challenges. The actual operators people use, so the unitary operators, have too much depth, meaning if you compare noise to the amount of operations you need, it's too much operations. Then, really big issue, too many measurements. If you count how often you have to measure, meaning how often you have to rerun your quantum computer, that really explodes massively, because you have to vary. You have to constantly rerun it and change your operator here. And then if the barren plateau issue hits in any way, the number of measurements explodes in a really radical fashion. And if we now think more concretely about how this is used for, let's say, a molecule, it's an issue that's often not so much discussed yet because although these three are already hugely problematic. Then let's consider we have here the kind of what's called an active space, the part that we map to the quantum computer. But somehow to make the calculation good, we have to do some kind of perturbation theory to include the rest. And then the measurements explode even further. So all really challenging. And while I would love to discuss also this last point a little bit, I will discuss maybe more these first three a little bit today. But now, you know, there is a reason why still people use variation algorithms, including us, all the time, because it's like understood, it's implemented. For small qubits, it produces results, you know, so there is a reason why we do it right now. And the key point is also, if you don't want to do it, we need an alternative approach. Yeah, and I guess given these challenges, it is worthwhile to consider alternative approaches. So now let's consider a different approach. And let's consider a little bit, what do we actually know about quantum computers and about quantum computers producing exponential speedup? In general, a quantum computer does not produce exponential speedup for trying to find the ground state of some quantum problem. You cannot construct a general algorithm that will generate exponential speedup if you ask it to produce you the ground state energy. The proven exponential speedup is for time evolution. So if we start with an initial state and time evolve it, here we have a proven exponential speedup that is also, once you look into it, really easy to see why. So we have to start to think about, okay, we want to time evolve the system, and that's it. Then we have proven exponential speedup. And then we want to get, and this is of course the challenge, we want to get all relevant properties we're actually interested in about the quantum mechanical problem. We want to get it from the time evolution. That's of course not how you do it in quantum chemistry. So now we have to think a bit about how do we do this. And the way we go for this is that we time evolve it to an equilibrium state. And to get there, to get through time evolution to an equilibrium state, we need to kind of consider the system in a way that they are in nature as an open quantum system. Meaning, as you time evolve, there has to be the possibility of relaxing energy into an environment. And then you just time evolve and go into an equilibrium state at some temperature. So let me, like now very vaguely, I will get much more technical about this, but let me just very vaguely draw this up, how the idea is. We say, okay, you know, we want to simulate some quantum system and give it the possibility to relax energy into an environment. Now let's map this to the quantum computer and let's consider the fact that actually we need to use, there are no others, we need to use noisy intermediate scale quantum computers. They are noisy. What is the source of the noise? The source of the noise is an environment. And the interaction of the qubits, the ideal qubits with this environment. And so we map the quantum system that we consider and its environment to the quantum computer and its environment. And by this, we achieve several things. One is, of course, we include the decoherence. That is normally a problem for what you want to do on a quantum computer. We include the decoherence as part of the problem that you want to solve. There's an additional interesting fact. If you think about how powerful is your quantum computer, you could conclude that if you treat it as an open quantum system, it's more powerful. This is because if we want to solve open systems on a classical computer, it's more difficult than closed systems. Now we go from time evolving the quantum state, the state vector, to time evolving the density matrix. So this has a squared number of entries. Therefore, we could conclude, okay, you know, the quantum computer in some sense becomes more powerful. Instead of needing 60 qubits for quantum advantage, we could, for example, do it with 30. However, we also have to be honest, you know, I mean, many efficient approximations exist if you have strong decoherence in your system. So now you have to balance these two against each other. I will today talk about, of course, the more exciting point, the first point, how we do it, and hope that it's exciting. But we actually also at HKS put a lot of work into this second point to check actually that we do not have, you know, efficient approximations coming about through the decoherence. But let me also point out, you know, by directly comparing these two things against each other, you directly consider the fact that the quantum computer is noisy and has decoherence. And that is also very different from basically any other complexity work that is done right now, because basically any algorithmic study that you see kind of ignores the fact that the quantum computer is noisy, or if they do not ignore it, they maybe kind of, you know, roughly make an estimate, of course. But here you can basically directly consider the fact that the quantum computer has decoherence. So, you know, a lot of issues, of course, practical issues arise once you want to do this. Like the first one is the one I want to, let's say, spend quite some time on. How do we effectively describe the environment in a gate-based quantum computer? Of course, there are other issues, you know, what if finite fidelities and errors are a result of miscalibration? This is something we have to basically exclude. We have to assume that finite fidelities come from decoherence. Hardware specific, how hardware specific is this? And what systems of interest can we really simulate this way? Today, I will give some very obvious examples, but actually we also consider how to map molecules, so fermionic systems, to this, but I will actually not discuss this today in this talk. So basically what we are working on at HKS is a workflow where you start, you know, on an actual problem, could be anything, and then lots of stuff happens, and in the end it gets sent to the quantum computer. But let me now go through, actually, because the technical interesting part is this here in the middle, and let me go through this a bit. So we start in an actual problem, and then we always currently transform it in what we call the open system model. So anything you start with, we make certain transformation to get it in the form of H0 equals a system Hamiltonian plus a coupling to a Bath Hamiltonian. So anything gets transformed. This system, being spins, can be any type of spin Hamiltonian with coupled spins or whatever. And I mean, the coupling can also be more general than this here. So I mean, any type of spin Hamiltonian can be HS. A coupling Hamiltonian to bosonic modes. And then basically a kind of non-directing path of non-directing bosons. So first step, take the actual problem and transform it into the open system model. Then we come from the other side in practice and look at the quantum computer. And of course, we know a little bit what type of algorithm we run on the quantum computer. And out of that, we produce, and we know, or we need to know, like single qubit properties like their decoherence rates. And out of this, we produce what we call the noisy algorithm model, which basically is a master equation where you have kind of your coherent time evolution coming from Hamiltonian. It can be many things. I write it down here as H system to be reminiscent of the open system model, plus maybe additional degrees of freedom. And some type of Lindblad-like terms that are basically the transformed decoherence. And then in the end, we try to bring it all together. Yeah, so we try to take, we have now a nicely abstracted open system model, we have the noisy algorithm model, and we try to bring this together. And now I want to spend some time and really get technical. So far it was all very high level. So let's now really go technical and think about how we derive this noisy algorithm model. All right. So, you know, we put in the fact that some type of Hamiltonian and an algorithm to create the time evolution under this Hamiltonian. And what we want to get out is some static master equation for the noisy algorithm model, which consists of like the coherent time evolution under the Hamiltonian plus additional Lindblad-like noise terms. All right. Let's remind ourselves how, in general, how does an algorithm to create a time evolution under Hamiltonian look like? You have a Hamiltonian, you rewrite it into a sum of kind of smaller terms that don't compute, by the way. I mean, these HKs don't need to compute, yeah? But you rewrite it into the sum. Then you look at each of these kind of terms that act on a smaller Hilbert space and think about unitary operations that will, in the end, create you this type of time evolution. And then, so you say now you want to have kind of a time evolution, which is like small time steps t, and you want a capital M of them. Okay, so basically you apply capital M times always your time evolution operator. And then a key point is that t is small. So now if we put in this sum from here, we approximately, take the sum out of the exponent and get a product again. This is the Trotter expansion. And then we have the full time evolution that we wanted in the beginning, because now we can hear each of these ones we can represent by these unitary operations that are some gates or something. All right. Basically, if you think about how we construct this use, there are various types of things that goes in that I will not discuss in detail, but of course you have to consider it. One is what is the connectivity of your qubits, and the two type of cases that we consider in practice is all-to-all connectivity, so every qubit is connected to every other, or linear connectivity, so every qubit is just connected to the nearest neighbor. And while linear connectivity might seem little, there is actually a really nice algorithm, which we always call swap algorithm, because you swap it, that is super efficient, even on a linear geometry. So basically, yeah, so you consider your geometry, and you consider what kind of gate sets you have available, C0s, or maybe Molmer-Sørensen or whatever, and construct this use. But now, of course, additionally, what you have to consider is, I mean, this is not unique. So, there are various unitary operations that can produce the same effective kind of part of the coherent time evolution. But now let's consider what the noise does. So, yeah, absolutely. Yes. Yes. Yeah. No, please, let's do questions in between, Sure. Yes.
Does it work? I guess so.
I guess so. We hope for the best.
Yeah. So you said about the swap algorithm.
Yes.
So it was pretty efficient.
Yes.
But nevertheless, I guess in 2D, if you have a term between, somehow it will increase a lot the number of operations that you add to your time evolution. So in what sense is it efficient?
So if you have a spin system that has all-to-all connectivity.
Oh, in that case.
Wait for it. You have all-to-all connectivity in your spin system, and you map it to an algorithm on a quantum computer that has also all-to-all connectivity. You need one of these Trotter steps has n linear depth to perform it. If you map it to 1D and it has all-to-all connectivity, the original has all-to-all connectivity, your computer has 1D, you still have n depth. I know that sounds amazing, and it is, because all-to-all connectivity actually, if your quantum computer has all-to-all connectivity and the system you consider has less, you can become sublinear, okay, which is also fantastic, getting sublinear. But you never go beyond linear depth, even on a 1D architecture. And that's what I mean with very effective. Yeah. And that is, so that is particularly, and it's particularly true for fermionic systems where even all-to-all connectivity doesn't actually help you to improve it. Anyway, but so connectivity is not such a huge concern actually in practice. But of course, if some people give me all-to-all connectivity in their quantum computer, I'll take it. I'm not against it. So now let's define a little bit kind of how does the noise in the quantum computer look like. There is the actual quantum computer, you know, where you have, let's say, your qubits, you apply gates and all types of things. And each of the qubits is individually coupled. I mean, that's at least the assumption. Of course, you can relax that assumption and do whatever you want, but let's say normally you take local noise. So there are, you know, some decoherence terms for each qubit, some decay terms for each qubit, something like this. And in the end, where we want to go to, so this is like the actual quantum computer. And now we want to go to something where we put in this kind of coherent time evolution, but we want to come out with something where we have the coherent time evolution and the kind of Lindblad term time evolution, yeah, some noise time evolution. And so for each of these kind of parts of the Trotter step, and this all adds up in the end again to some continuous time evolution of this form. So where the Hamiltonian adds up, I mean, because t is small, and all these terms add up because t is small, and you have this continuous time evolution. Let me just think if I need to say something additional here. So this is, yeah, so this is basically where we want to be at the end. Now, let's look, here's the kind of physical thing that the quantum computer actually does. And this is where we want to come out. So how do we get from here to here? Okay, so here is where we want to end up with. Now let's consider. We have here one of these terms, you know, with a small t. And we kind of actually implement it by making various gates one after another. In practice, kind of to model the noise, and this is a good model even if your gates take time. We say there is noise, then there is the gate, then there's noise, then there is the gate. Of course, you can rewrite this into a more general fashion in basically having the noise during the gate, but then you can again rewrite it into an effective gate and the noise. So noise, gate, noise, gate. And the one thing I want to actually point out is I've written this in a super operator way. So all this here is super operator writing. People might not be super familiar with, but you know, it's just basically the math equation in the exponentiated form. So it's just consider it this way. So noise, gate, noise, gate. And you know, now we want to have all the noise here in front. Yeah, so we want to commute this up front such that we can all add it up back to one kind of big noise term. And then all these U's again add up to this kind of coherent time evolution. So what we need to do is we need, for example, to take this kind of noise term, like written here, and commute it, you know, commute it to the other side of the gate. And that's it actually. So we need to take all of those and commute them through. And then of course we need to rescale the time in some kind of obvious fashion. I mean, you have the time that your actually gate takes, which is tau, and you have a time that is the one in your that you want to have simulated, yeah, and kind of there's a connection between these times, and that actually rescales the decoherence rates, which also leads to some kind of way you can kind of know how to choose your kind of Trotter step time in a way that is optimal. So basically, in the end, what's going to happen is you're gonna take all the noise operators that are in this noise term here, noise operators O, and since you commute it, you have to basically transform them with these unitary gate operators, you know, that you have computed. And one issue that appears is basically there are often, or let's say if you can have them, sometimes you have what's called small angle gates in kind of a Trotter expansion that basically means you can just ignore it, this transformation, and just keep your original noise operator. But often also you use what's called large angle gates. And I will show this in a second, an example for this. So let's say, for example, one of your operators that you have in kind of when you create a time evolution is a Hadamard gate. Sorry. Okay, so the time evolution that you want to create is the one under sigma x. Your noise operator is sigma minus. So now if you kind of create this type of unitary operator, you do it by making a Hadamard gate. I mean, it's one option. There are many options, of course, but you could, for example, do it by creating Hadamard gate, then a phase gate with a phase of 2t, and again a Hadamard gate. And now let's say you have here your noise operator, kind of your noise with the noise operator sigma minus coming, and now you want to commute. So you have your three operators, and now you want to commute your noise term, with this Hadamard gate here in front. So what happens? You have to now calculate the effective noise operator by transforming your original noise operator, and outcomes, out of sigma minus, you get sigma minus minus I half sigma y. Yes?
Do I understand correctly that L1F, so the effective Liouvillean?
Yes.
So it's not the same as OF, O effective, right?
No, O effective is just the operator. That is, each of these Liouvilleans is described by operators like O, rho, O, yeah? So the O effective is the operators of the L effective. Okay? Yeah. And let me now just, show some example where we have a linear chain of qubits, or let's say a linear chain of spins. And you create the time evolution on the quantum computer of kind of this Hamiltonian. Your Lindblad noise in the quantum computer is pure damping. So meaning all your operators are damping operators. And what you do is you kind of calculate the effective time evolution of this and compare. So we show one simulation, the black line, which is the gate-based quantum computer, now where we kind of calculate what the gate-based quantum computer would do by calculating, the gate, then the noise, and the gate, then the noise, and so on. So it's all gate-based here, and we do the Trotter expansion, and so on and so on. And here, for this, we solve the noisy algorithm model, meaning we just use Q-tip and solve the mass equation. And it fits excellent to each other. So basically, we have now shown how we can take, if we know that it's supposed to evolve a quantum system, time evolve it, and get out the noisy algorithm model. So now, let's remind ourselves, why did we do all this here? Yeah, the goal is, that we have now a kind of easy to write down model for what the quantum computer with all the noise and the decoherence and so on is actually doing. So now we have it. Now we can look at it and see, can we map this here to any interesting problem that we are interested in? And now let's consider an example for doing that. So what we now want to do is we want to start with an actual problem. However, when I say actual, well, you will see, I keep it quite abstract. In some sense, we jump directly to the open system model. And then basically we know that the quantum computer is described by the noisy algorithm model. And then we try to bring this together. So the type of examples, that people do when they consider, the past, when they considered open system models, are often related to photosynthesis, and coming out of this idea that photosynthesis is an interesting topic to study, organic solar cells. That's a typical problem where you have some type of big macromolecule, and it's maybe not even that big. So let's say you have a molecule, and it has different subparts, and light can create in one of these subparts an exciton, and the exciton can jump through to some kind of reaction center. And what you then normally want to do is, in photosynthesis, you just want to study how this happens. And if you have an organic solar cell, you want to actually optimize that every exciton created arrives at the reaction center in the minimum amount of time, and that no other relaxation processes or other things kind of actually relax the energy into some other degree of freedom. So that is what you want to do. But now, let me simplify this for now to actually make it even simpler. We take only one of these sides, which basically means we have a side where you have kind of not excited state and an excited state. And this green bubble here means that we couple it to some type of vibrations, aka bosonic modes. And so now we actually directly arrive at the paradigmatic open system model, the spin-boson model. And now there are some hardware requirements if you want to consider this. So basically what we would like to have if we want to do this, we want to have qubits. We want to have a big chip, and then the qubits have various, differing decoherence properties. And some of the qubits, in our case, one, should be very good actually. And the others, can be, let's say, normal. If your qubits are bad, I mean, it's also not very good, yeah. But let's say some should be kind of normal, and some qubits should be actually very good. This is actually the case in superconducting devices. There is a whole range of different decoherence rates once you look at a chip. If you would want to implement this with, for example, ion traps, you could also use, for example, lasers to create stronger decoherence in some of the qubits. But I'm not a huge fan of this, of course, because normally decoherence is already so large that we don't want to increase it. Yeah, but anyway, so there are various possibilities to generate a situation like this. Yeah.
Can you give some examples of what is actually a very good qubit?
Yes. So basically, the rough estimate that we always put in when we do simulations and so on is that we want to have the very good qubit. We have 2 qubit gate fidelities of 99.9, and normal means 99%. So I would say also the normal ones need to be pretty good given current standards. But this is the thing. If you go worse than 99%, I can show you that I can create methods that can efficiently do the same on a normal computer. I can use the decoherence to do similar kind of calculations on a normal computer. And let me point out, this is kind of we have actually ways to relax the need for very good qubits completely, but that would be a bit too much for today. But let's say this would be an ideal situation. You have some very good 99.9, or 1 or 2 or 3, let's say, and then a big option of not so good, let's say 99, maybe some lower, but if it goes lower, it's not so good. Okay. We also, for this talk, I make some strong assumptions on the availability of specific 2 qubit gates, but that is not, that's not strictly necessary. You're actually quite flexible. So now what do we do? Let's say we have this good qubit, and we couple it by turning on, a 2 qubit gate or something. But let's now consider static coupling. We just couple it to a normal qubit. What does that mean? This perfect qubit sees in some sense an environment caused by this normal qubit, and the spectral function of this environment is seen from the perfect qubit is kind of this Lorentzian, where the frequency omega-0 is the, or epsilon, yeah, we call it, omega-0 is the frequency splitting of your qubit, and this kappa is the decoherence rate of your qubit. Yeah, so that is the kind of spectral function that your qubit sees if you couple it to a normal qubit. Now, knowing this, let's now see how we, how we do this mapping from noisy system model. And okay, so one key point also to emphasize is I'm allowed here to consider this as a static coupling because we have already gotten rid of the quantum computer in some sense. We are considering the noisy algorithm model, so everything is static. Yeah, I can put in a coupling between 2 qubits in my original Hamiltonian, look at the quantum computer, derive derive the noisy algorithm model. Now everything is static. So I do not have to consider gates in anything anymore. Okay, so now let's start. This is a spin-boson model, yeah, the open system model I had before, just with one qubit, very simple. One qubit, coupled to bosonic modes, 3 bosonic pair. Okay, it's clear, yeah? System gets mapped, you know, one system spin gets mapped to one system qubit. Okay, it's very clear. The good qubit is the qubit that we will use to describe this up here. But now, what else do we do? We have here these bosonic modes, yeah? And what we actually do is, is a continuous pair, because the open quantum system. So it's a continuous, as a continuous spectral function. And what we do, instead of having an infinite amount of bosonic modes, we take a few bosonic modes, each of them being broadened, and add them up such that in total, they give you the same spectrum that you would get from your original path. Then, instead of taking bosonic modes, we map each of these bosonic modes to several qubits. So basically, you have n path qubits. So n of these normal qubits. And let me give you an example. So basically, kind of the bosonic path of the spin-boson model is always described by some spectral function. And this is, for example, shown here in black. So this is the ideal spectral function that we would like to have in our original open system model. And now how do we recreate this on the quantum computer? Yeah, let's say we have 6 qubits and do a fitting here. And here, this issue comes back that I showed before, that we consider these Lorentzians. Yeah, so we consider it Lorentzians and fit these Lorentzians because we can manipulate these coupling terms here. We fit it to the spectral function that we want. And then basically we have it all. We have kind of, the system is the good qubit, the path are the normal qubits, and the coupling is something we can adjust by originally choosing our algorithm on the quantum computer in the right way. Yes, absolutely.
So the am I correct that here the broadening is something fixed because it's fixed by the hardware?
Yes.
And so the degrees of freedom where you can play with are the couplings themselves.
Exactly. Yes.
And how do you play with them in practice? So is it because the 2 qubit gates between your noisy qubit and the perfect
exactly?
qubits
I mean, with a 2 qubit gate, let's say, you know, in practice, let's say you have available a C0 as a 2 qubit gate. Then in this kind of, if you make an effective Trotter expansion of something, you would always use 3 C0s to create any type of original coupling between spins. And that can have any strength, which makes sense. You know, the C0 like rotates the qubit completely. So, you know, you can make any type of strength in your original model. Yeah. That said, of course, you know, I mean, always in any simulation task on a quantum computer, if the parameters in your Hamiltonian would be hugely different. For example, the delta is 10 to the -8 and your G is 10 to the 5. Well, then there's no reason to simulate it. You should make an approximation anyway. Yeah. So all parameters should be of the same order of magnitude anyway to make it interesting.
Okay, thanks.
All right. Yeah. So now basically, now we have this complete mapping. And I mean, also let me bring this back a little bit now to the algorithm. Of course, you know, I said we have gotten rid of it. We just look at the noisy algorithm model. But, you know, in practice, of course, let's say you consider 1 qubit and want to map it to 4 normal qubits. Here, you know, also all connectivity would come in handy, actually, for this type of situation. That said, you can still, with relatively little connectivity, create a similar situation on a chip. Yeah, for example, you need 2 good qubits and you have your 4 normal qubits, and then you make the swap algorithm and always have like good qubit gates with the normal qubits, then swap and gate with the other normal qubits, and so on. So there are kind of adapted swap algorithms that are still pretty efficient, that allow you to map all types of situations on each other. And let me just show here an example. Basically, where we show the time evolution of a basically the time evolution of kind of the 6 qubits versus a spin-boson model solved in the non-interactive Flip approximation. And let's say for short times here, it's okay. Then of course for longer times, it's not perfect. And the reason for this is that, well, I mean, the quality actually is mostly limited by, not by the algorithm or anything, but it's actually limited by the kind of precision of the fitting of your spectral function. This is the major limitation of the accuracy. So everything else is basically works really well. Yeah, so it's always a question, how good can you fit the spectral function? And then, I mean, all the people who know and have studied this type of models, the long time behavior is often quite sensitive to the spectral function, especially at low frequencies. And let me just point out, without, let's say, doing too much here, but let's say maybe a couple of words. What is now if your system qubit is not ideal? Then actually what this looks like, it looks like an effective temperature. Yeah. So this, you can go back to your spectral function that you want to create and give it an effective temperature, so that even for negative frequencies, it has, let's say, some non-zero value. And then, okay, I don't show a result here, but then, I mean, if you have basically systems at finite temperature, you can even integrate, let's say, decoherence in what we call so far good qubits. Okay, let me really quickly now go through the photosynthesis example. I mean, I should come to an end anyway. And it's also not super different from what I just showed. But let's say let's say we want to really have 3 sides, you know, where your excitation jumps from one side to the next. Then, you know, you would go through all these steps. You have you need 3 good qubits, you know, and you have we simulate this here with the 6 bad qubits. We do the fitting of the spectral function and so on and so on. And basically get some type of time evolution and look at the time evolution. And I think the thing that normally is studied then in this type of models is kind of when does the excitation arrive on the side 3. Yeah, so you start with an excitation on side 1, and in the end it ends up on side 3. So you want to know how much, you know, and at which time scales you get your excitation to the last side. Sure.
So you simulate this system. So what is it exactly that you would optimize? So in the end, you want to build a better solar cell by
That's an excellent question. That's an excellent question. I mean, so let's say we, you know, I mean, our strength of work is to put it later on the quantum computer. But the type of things that people optimize is, if you consider these different sites, you can, you know, choose all types of small molecules that actually represent these sites. And they give you different hopping parameters, different vibrational modes that go into the spectral function and so on. And then you want to combine the kind of hopping and the vibrational modes and so on to get kind of maximum time. You want to have to go from basically this being excited, the third side response should be optimum. And you do it basically by, you know, I just draw these 3 dots, but they can be all types of actual molecules. And you change these molecules and hope for the best, be quickest at the end. And of course, instead of hoping for the best and doing all the experiments, getting experiment kind of simulation results first is, of course, probably really helpful. And, you know, a question that people ask, for example, what happens if in the same situation, not each side is coupled to some vibration, but they have correlated vibration. So now the bath is correlated. And with the same setup, you can also consider correlated bath. And, you know, it's like one interesting result that people have considered in the past. What then happens actually is that the occupation of side 3 is strongly suppressed. So this was one of the results that we just reproduced that is known from this type of studies. Let me now summarize a little bit. What I wanted to discuss is kind of this idea that you take, actually you consider things that you want to solve as open. So you always consider problems as open and try to map them to what we call the open system model. And then you also know that your quantum computer, it's very noisy anyway. And so you consider it that way and produce the noisy algorithm model, and then you bring this together. And in this way, you actually make noise or decoherence a resource that you use kind of to solve problems. And there are many steps and also many use cases that I did not discuss. Let me point out that on 22nd of November, we are going to make like a 5-hour webinar on all technical details involved in every step here, also including many more, use cases where you go from an actual problem to the open system model. And you can sign up to it. You also do not have to be there for all 5 hours. You can, it's a webinar, you can drop in and out if you want. But you can sign up for this on, oh, sorry, this is not FROMS, this is actually forms, like form, yeah. forms.cloud.quantumsimulation.de. If you want to sign up to it, do not hesitate to do that. So yeah, forms, not FROMS, forms.cloud.quantumsimulations.de.
All right. So
that's it.
Thanks,
yes, thanks.
So first of all, is there any question on Zoom? Not now, I guess. Saad, please.
Okay, thanks a lot for this very interesting talk. Introduced there. I'm really glad that you try to turn the enemy into an ally here with the noise. That's a very nice point of view. I've been really interested in open quantum systems or in quantum computing, so in my career. And now I have a question for you. That is, it seems that you're focusing on specific cases where you derive a microscopic model that is based on the Born-Markov approximations in the end, when you build the Liouvillean.
No, that's a very important actually, because it would be super boring if we only would consider Born-Markov cases, right?
Okay.
Let's just go back here to the very beginning. Because let me go here. The model is so what we do is we start from something and come to the open system model in this form. And this part here, the spectral function of this does not have to be flat or anything. Of course, in practice, there are limitations to mapping it later. But the trick that I did of representing this with broadened modes means that we can have very much a structured spectral function. That is a key point, that we allow for structured spectral functions. Of course, in practice, if you look at the classics of open system models like subohmic spectral function, that's, if you have a sharp cutoff, I don't know, I cannot deal with it because I have Lorentzians. But generally, kind of structured spectral function where you have peaks in it are absolutely what we're going for here. So we are not considering this as something that you have to solve within a Born-Markov approximation. Huh?
Okay, so means that naturally, if you go this way, you can observe some exotic feature that we will call the non-Markovian features, like some recall of the, some memory effect in the bath,
yes,
and some signatures. Is it something that you can also like simulate with your approach and that you observed? Sure.
Definitely. In the case that I showed for the photosynthesis, you see memory effects. You see excitations come back and so on. Yeah. So that's something that this would do on a quantum computer. Of course, also then you have to compare to the best classical methods, of course, which can be challenging. But yeah, definitely that is something. Having non-Markovian baths makes it interesting
Thank you.
Yeah, thanks. Sorry, but it was your first part to talk, but it was almost the same question. So I will rephrase my question. In when you do the system-based separation, I mean, usually the spectral density, when you consider a real system, are very structured.
Yeah.
So is it more favorable in this case, since you were mapping, let's say, some qubit with what you call normal, which could give maybe more easily structure spectral density instead of ohmic one or subohmic one?
Okay, okay. There are two ways to address this. One is, in the end, we want somebody to just define what they want. It should be interesting to them, and we do the best in the mapping. Okay, so people should not think about. They should just define an interesting problem to them with any spectral function, and then in the background we kind of get the mapping done with a certain quality. Now we can ask, how good is this quality, and for which cases is this quality good? And then, having for what is particularly where would the quantum computer be particularly good? And then having nice structure, with peaks and so on, is I think the more interesting case for the quantum computer, the more stronger where you would rather achieve quantum advantage on the quantum computer. Then ohmic is also not too bad, but for example, ohmic at 0 temperature with this typical problem, at 0 frequency, is a case which you cannot really nicely map, or the long time dynamics does not map nicely to the quantum computer. You will always have quite a bit of error at that point.
Okay, thanks.
Yes. So what if my actual problem is not a qubit coupled to a bosonic path, but to a fermionic path?
Oh, if it's a spin coupled to a fermionic path.
Or a fermion coupled to fermions.
Okay, let's start with the spin fermionic, because I can answer that very clearly. All right, we have if you have it already in that form, then you have to note that a spin always has to be coupled to C delta C, to annihilation and creation. Then you look at this. C delta C commutes with C delta C, with other C delta C, like 0, meaning bosonic. So you can make, again, for this an approximation, which we call often bubble approximation, and sometimes it's similar to a random phase approximation, and do exactly the same steps, all bosonic, like this. Yeah. Now, if it's fermion to fermions, of course, now it gets really tricky. Yeah. And we starting to address it, and in the webinar on the 22nd, we will talk about it. But it's tough. Yeah, it's a lot of work to get that done. And to make, especially to have the approximations that you do controlled in a fashion that makes the overall workflow really interesting. Yeah.
Is there any from the audience or in Zoom? Apparently no. I have one question actually from almost the very first sentence of your talk, when you said there is no quantum advantage to find the ground state energy maybe of your problem. I wonder, quantum phase estimation is not supposed to.
No, of course. Of course. Okay, so let's say actually there was, like earlier this year, there was a big paper that tried to address this question. And I don't know, it came out with a wake. You cannot fully address it. So my conviction is when we have a full error corrected quantum computer with phase estimation, it will achieve quantum advantage and exponential speed up, even for finding ground states.
Okay.
Yeah, but for ground states for physical systems, because it will be able to find it for physical systems. Now, because we will be able to kind of approximate it an initial state with kind of polynomial overlap and so on and so on. So all these type of things will work. But what you cannot do is you cannot create an algorithm that deterministically for any Hamiltonian will give you in polynomial time the ground state. Now this is not possible. But these questions, taking a physical system in nature and finding the ground state, or constructing an algorithm that for any Hamiltonian gives you ground state are are similar but not the same. Yeah.
Okay. Thank you.
But for the same Hamiltonians, your open system also doesn't work. It's like the things that don't thermalize.
Yeah, no, I mean, it's a good
I
point.
mean, you
I-
also don't have an algorithm for
I-
any kind of thermal, which is bonkers,
Exactly,
right? Yeah.
exactly. No, I agree. Systems that don't thermalize, well, don't thermalize, so they never go to equilibrium. So in some sense, of course, what you could say, if you have a material in nature that has this property, then you would still want to study it just as it is in nature, meaning in its non-thermalized state. And then you could do it like here. But I completely agree. Yeah, I mean, spin classes that exist in nature do not thermalize on a reasonable. That would happen here as well. Yeah.
Okay, if there is no more question, we can thank Mike again for this very nice talk. And the next speaker can come to stage.